Hello, my name is Chas McGill, and I'm here to talk to you about the molecule representations used in RMG. So, the first way that people will usually interact with the molecule representations in RMG is through the RMG input file. So, in the input file, we have to specify the species that we are using for our model inputs. The species function has three required arguments, or three arguments. It has the label argument, which is a string input. This needs to be consistent for a given species throughout all of your documents, all of your files. You need a structure representation, and you need a indication of whether the species is reactive or not. So the structure representation is what we're talking about here today. There are multiple ways to represent this. You can represent it as a adjacency list, shown here. You can represent it as a smart string, a smile string, or an inchy string. So on the right, I've got an example shown where I've gone to the RMG website, to the molecule search function, and I've entered in ethane and drawn the molecule in order to get the inchy, smiles, and adjacency list representations for ethane. So this is a useful tool for getting the representation so you can use it in your input file. Now, SMILES is a acronym shown there, is a string representation of the molecular graph for molecules that we're using. One of the important things about this is that hydrogens are usually implicit in SMILE strings. So we have shown here methane just as carbon. The 4 hydrogens in methane are implicit there. Same with the 6 hydrogens implicit in ethane. All you've got is the bonds between the heavy atoms in there. This can lead to things like just O being water, or just S being H2S, which can be surprising and confusing, so be careful with that. Also represented in SMILE strings are ring notations. So we have the SMILES for cyclohexane here, with the 1 in that string indicating the start of a ring, and the second 1 indicating the end of it. With rings, if you see your elements in lowercase, that's indicating aromaticity. So that's the difference between cyclohexane and benzene here. You can also have multiple rings going on at the same time, like for naphthalene shown here, where you have a 1 ring and a 2 ring going on in the string. So SMILE strings can be used to represent lots of different molecules of incredible complexity. One way to interact with SMILE strings in a way that's pretty accessible is using drawing programs like ChemDraw or Marvin Sketch. If you take a SMILE string and copy it and then paste it into a drawing program, it will show you the structure of the associated with that SMILE string. You can also go in the other direction. You can draw a species in the program and then copy as that species as a SMILES to put the SMILE string into your clipboard. So this can be a really useful way to find out the SMILE string for a molecule that you know what molecule it is, but you don't know how to find the SMILE string for it. Something to be careful with here particularly is that SMILE strings are not unique identifiers. So a SMILE string represents 1 molecule, but 1 molecule can have multiple SMILE strings that represent it. So this is not useful as, say, a key function or something. So be warned, especially with things like aromaticity, that the representation that you pull from a drawing package may not be the same one that you see for it elsewhere. All right, the next representation we have here is the adjacency list. Um, so we have shown here, for an example, ethylene uh, and an adjacency list block. So the different columns in the adjacency list are providing you with different bits of information. So the first column is the atom index, here going 1 through 6. The second one is the element name, carbon, hydrogen here, but any atomic symbol that's supported by RMG can be used there. Then you have unpaired electrons. So if you had a radical, one of those would be U1 instead of U0, followed by electron lone pairs. So if one of these atoms was nitrogen, then it would have presumably one lone pair. It would have P1 instead of P0. Followed by charge. So this is kind of the local formal charge at an atom. And then the last entry in the adjacency list is a listing of different bonds in the molecule. So this has two parts. The first part is the bond that atom is bonded to, by the index number, and the second part is the type of bond it is. So S for single, D for double, T for triple. Now, full or fully defined molecules are not the only things that we use adjacency lists to describe in RMG. We also use functional groups. These are not fully defined and can represent multiple molecules for a given adjacency list structure. So this uses things like square brackets for lists of options, or R in place of unknown groups, or X as a wildcard in place of unknown quantities. So I have on the right here an example of an adjacency list for a functional group entered into our draw functional group function on the RMG website. This function has a lot of flexibility and could be any of these multiplicities. Any atom non-hydrogen could be at position 1. You have a lot of stuff going on here. And the result is that you have a lot of things that it could be. So you would use this like in the database and for the various tree functions that we have in RMG. Now, I mentioned multiplicity there. That's worth going back and specifying. Multiplicity is referring to the spin multiplicity of the molecule. So for multiplicity 1, this is for a molecule where it's existing in the closed shell. All of its electrons are in fully completed bonds or in paired lone pairs. Multiplicity 2 is for when you have a single radical species. You have one unpaired electron in the molecule. And multiplicity 3 is for a biradical, where you have two unassociated radicals in the molecule. If your multiplicity is not specified, then RMG will default to assuming the multiplicity is 1 plus the number of unpaired electrons. So with that, I'm going to close out this discussion. I'd like to thank all of you for joining me and learning about the representations used in RMG.